Hello everyone, and thanks for joining us on today's webinar on integrated shark fin antenna for automotive applications. My name is Amin. I'm an Alpha Application Engineer at EMWorks. So before we start, I would like to give you a short summary about what we are going to discuss today. So first, we'll talk briefly about shark fin antenna components along with some benefits of using such antennas. Following that, we'll have a discussion on some of the antenna design challenges. At the end, we'll have a live demo. If you have any questions, I'll be happy to answer them at the end of the presentation. Before we go ahead, I would like to give you a short introduction about our company, EMWorks. EMWorks is an electromagnetic simulation software company based in Montreal, Canada. We cover both low and high frequency applications. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a very wide range of applications, ranging from electric motors, transformers, and power electronics, to antennas and various wireless circuits and components. Alright, now let's talk briefly about the components of shark fin antenna. The main component of shark fin antenna for automotive applications can vary slightly depending on the specific design and functionalities incorporated by the manufacturer. However, here are the typical components found in shark fin antenna. Firstly, we have the antenna elements. They play a crucial role in receiving and transmitting electromagnetic signals. They are tuned to specific frequencies associated with various radio bands, including AM, FM, satellite radio, GPS, and other communication technologies. Another component is the amplifier. They contribute significantly to the antenna functionality by boosting incoming signals. This enhancement is particularly critical for weaker signals, ensuring that the antenna can effectively capture and process the desired radio frequencies. Next, we have diversity systems. Utilizing multiple antenna elements can enhance the quality of the received signal. This is valuable, especially in environments where signal reflection or obstruction can impact communication. Ground plane and housing are two additional essential elements of the shark fin antenna. Ground plane is often integrated into the vehicle roof. It acts as a reference point for the antenna. Moreover, the protective casing, or in other words, radome, is designed to be aerodynamic and weather resistant, safeguarding sensitive electronic components from environmental factors such as rain and snow. Next, we look at some applications of the shark fin antenna. Shark fin antennas find diverse applications across automotive technology with notable functions in AM, FM, and satellite radio reception. The antenna elements are finely tuned to capture signals in these frequency bands, ensuring optimum performance for terrestrial and satellite radio broadcasts. Additionally, the shark fin antenna plays an important role in GPS navigation system, where precise signal reception is essential for accurate location tracking. Its design allows for effective communication with GPS satellites, contributing to reliable navigation in various driving conditions. Moreover, the shark fin antenna serves as a channel for in-car Wi-Fi connectivity, enabling passengers to stay connected on the go. Lastly, V2V or vehicle-to-vehicle antennas play a crucial role in modern automotive communication. They enable real-time exchange of information among vehicles on the road, contributing to enhanced road safety and traffic efficiency. By using shark fin antenna, V2V antennas ensure reliable and effective communication, facilitating features such as collision avoidance, traffic coordination, and other driving applications. Now that we have explored some applications of shark fin antenna, let's look at some benefits of using shark fin antennas. Using shark fin antenna in automotive applications offers several advantages, contributing to improved performance, aesthetics, and functionality. Shark fin antennas are designed to house multiple antenna elements within compact housing. This allows for the integration of various communication functionalities without the need for multiple external antennas, optimizing the use of available space on the vehicle's roof. Moreover, the modern and sleek appearance of shark fin antennas enhances the overall aesthetics of the vehicle. Unlike traditional whip antennas that can be visually obtrusive, shark fin antennas contribute to cleaner and more sophisticated vehicle exterior. Now let's dive into some challenges with shark fin antennas. We all understand how important antennas are for vehicle communication. While shark fin antennas offer numerous advantages in automotive design, they do come up with some challenges. Space constraints can be a significant issue since integrating multiple functionalities within compact structure can be difficult. Vehicle body interaction enters another concern, as the placement of the antenna and its interaction with the vehicle body may impact performance. The integration of multiple antennas in confined spaces may lead to interference among different antenna elements or other electronic components in the vehicle. Additionally, the use of radome, while providing protection, can produce challenges related to signal transparency, potentially affecting the efficiency of the antenna. Addressing these issues is critical to ensure the optimum performance and integration of shark fin antenna in modern vehicles. Utilizing advanced 3D EM modeling techniques enables comprehensive understanding of the antenna behavior in real automotive environment. Alright, now let's look at an example of shark fin antenna. As we can see, the shark fin structure consists of 3 antennas, namely GPS, Wi-Fi, and V2V antennas. Both Wi-Fi and V2V antennas are printed on FR4 substrate. GPS, however, is printed on Alon AD1000 substrate, which has permittivity of 10.2 and loss tangent of 0.0023. The antenna has total dimension of 174 mm by 120 mm by 1 mm. In addition to the 3 antennas, we also have radome. It is used to protect the antennas from various environmental conditions. Now let's study the performance of the antennas without radome. As we can see on right, we have shark fin antenna on the roof of the vehicle. Also, we have a driver inside the car. Now let's study the return loss of the 3 antennas. So as you can see from the graph on the left, GPS antenna resonates at 1.57 GHz, whereas Wi-Fi antenna resonates almost at 2.4 GHz. V2V antenna resonates almost at 5.9 GHz, as you can see. On right, we can see an electric field animation at 2.4 GHz. The next important parameter to study is the insertion loss. So basically, you want to make sure that when the antenna they're operating, they don't affect each other's performance. So as we can see from the graphs on the left, the antennas, they have less coupling between each other. So for instance, for the GPS antenna, there is less coupling from the other 2 antennas, namely Wi-Fi and V2V antennas. So for instance, for the GPS antenna, we can see that the insertion loss is almost around minus 30 dB. And this means that the 3 antennas are well isolated at this frequency. Now let's study the 3D radiation pattern of the antennas. On the right, we can see that the GPS antenna has maximum gain of almost 5.6, while Wi-Fi and V2V antennas has gain of almost 8.9 dB. Now let's study the operation of the antenna with radome. So basically we want to study the effect of the radome on the operation of the 3 antennas. On the right, we can see a shark fin antenna which is covered with the radome. So first, let's study the performance of GPS antenna with and without radome. So as we can see from this image, the radome has almost no effect on the performance of the GPS antenna. Similarly, for Wi-Fi and V2V antennas, there is not much variation introduced with the use of radome. Now let's look at the effect of radome on the coupling between the antennas. So first let's study the coupling between GPS and V2V antenna. So as we can see, there is almost slight variation in terms of the coupling between GPS and V2V antennas. Similarly, for the coupling between GPS and Wi-Fi, we can see that there is slight change in terms of the coupling between the antennas. So basically, the radome has slight effect on the coupling between the GPS and Wi-Fi antenna. Lastly, we can see that the coupling between Wi-Fi and V2V is similar to that one of without radome. Alright, now let's look at the SIR. As the antenna now operating near the human body, we want to make sure that the operation of the antennas cause no harm on the human body. So for this, we study the SIR. So as we can see, that the SIR of the human body is almost 0.010, which is below the recommended level of 1.6 watt per kilogram. Now let's study the effect of radome on the 3D radiation pattern for the Wi-Fi antenna. So as we can see from the image on the left, the gain of the antenna was initially 9.2 without radome. When we use the radome, we can see that the gain of the antenna dropped to 8.9 dB. But still, the radome has no big effect on the 3D gain pattern of the antenna. Lastly, let's look at the 3D radiation pattern of the three antennas with and without radome. By looking at the three plots, we can see that the use of radome has no effect or has small effect on the radiation pattern of the three antennas. Welcome again in this live demo. In this demo, we'll show you how to design and simulate such antennas using HFWorks. As we can see, HFWorks is fully embedded inside SolidWorks. Once you finish creating your geometry inside SolidWorks, you can just go ahead and start your EM simulation using HFWorks. So it's just simply a tab. So basically you don't need to import any CAD geometry. In HFWorks, we have four types of studies. We have antennas, S-parameter, TDR, and resonance. But today we'll focus on antennas. Like any other electromagnetic simulation software, we usually have three main steps. First, we need to specify the frequency range, apply material, and then set up the boundary conditions. First, let's start with the frequency settings. Once you right-click, you click on Properties. Under this table, we can specify the level of accuracy, whether it's normal or high accuracy. We can also specify whether we are only interested in port solution or also whether we are interested also in the 3D field data. Next, we need to specify the type of sweep. We have different types of sweep. We have discrete, fast, single point. Also, you can import your frequency point from a file. For this study, for instance, we have the start frequency is 1.49 gigahertz and the end frequency is 6.9 gigahertz. We have 51 frequency points. As for the meshing, we have two types of mesh. We have manual and adaptive. So for adaptive, basically the software will try to find the appropriate mesh for your structure. If you are an experienced user and you want to save some time on the meshing time, you can use the manual mesh. Also, if you are interested, for instance, in studying the temperature distribution in your structure, you can click on the thermal coupling. In HFWorks, we have our material library, which consists of material with predefined properties. So for instance, for substrate, we have different materials which come with predefined properties, as you can see. You can also create your own material library or import one if you have it. So to apply material, you simply right click and you say apply material, and then you specify the material that you're interested in. So to edit the material properties, again you right click and say edit material. In this table, you can edit the material properties you're interested in. For instance, you can change permittivity, loss tangent, permeability, or magnetic loss tangent, along with other parameters. So back to our design. So we have our antenna, and we have the Wi-Fi and V2V antennas that are printed on FR4. Also we have the GPS antenna, is printed on the Arlon material. Also we have the driver. So maybe now I need to show the car. So also we have the car, which is made of PEC, as you can see. And also we have our radiation boundary, which is the air. Maybe I need to change transparency. Yeah, so now we can see the driver, the car, and also the shark fin antenna. Maybe I need to hide the air for now. Next, we need to set up the boundary conditions. In HFWorks, we have different boundary conditions, such as port, lumped element, PEC, PMC. Also, we have the radiation boundary. So in our example, for instance, we have the wave port, which is used to feed the GPS antenna. Also, we have a lumped port for both the V2V antenna and the Wi-Fi antenna. Also, we have the radiation boundary, which is the air. Maybe I can show the air. So this is our radiation boundary, as you can see. So now let's look at the mesh control. In HFWorks, we have the option of applying mesh control on different entities. For instance, we can apply mesh control on bodies. Also, you can apply mesh controls on faces, like this one. Also, you can apply mesh control on edges. We can also specify the element size. So now, for instance, let's see the mesh of our structure. So if we right click on the mesh and say show mesh, so now we can see the mesh on the car and also the human body. Also we can see the mesh on the antennas. So now we are done with the study settings. Now let's look at some of the simulation results. In HFWorks, we have what we call the results table. This table basically summarizes important circuit parameters such as generalized S matrix, renormalized S matrix, impedance matrix, admittance, port results, and VSWR. You can print result versus one frequency or all frequencies. Also, you can export results to different formats such as text, CIT, SPC, or touchstone. Now let's look at some 2D plots. First, let's start with the return loss. So for this, we can see that for instance, the GPS antenna resonates at almost 1.57 gigahertz. So following that, we have the insertion loss, which shows the coupling between the antennas. So to create such plots, you simply right click on plot and you choose 2D plot. So for instance, now we are interested in the case of the antennas without radome, no radome. So we choose for instance S11, S22, and then S33. So now we can see that the 3 plots. You can, for instance, save plots in different formats such as PNG or other formats. Also, you can see the results in tabular formats. As you can see, you can again save them in different formats such as text, OS, or CSV. Next, let's look at the radiation pattern of the antennas. Maybe I need to hide the car for now. First, let's look at the GPS. So this is the radiation pattern of GPS antenna, and this is the gain of the Wi-Fi, and lastly we have the gain of the V2V antenna. So to create such plot, you simply right click on plot, you choose polar plot, choose 3D polar plot and set fringe. And then for instance, for this we are interested in GPS, you choose GPS antenna and then we click OK. Sorry, choose the wrong one. Yeah, so let's choose GPS antenna. Yeah. So now we can see the gain of GPS antenna, but this is normalized value. So let's look at the 2D radiation pattern. So first we start with GPS antenna, and this is the Wi-Fi, you can see, and V2V. So to create such plot, you right you right click on polar plot and you choose 2D polar plot. So this time let's for instance plot the one for Wi-Fi antenna, and then you click add. So here we go. So you can see the 2D polar plot of the Wi-Fi antenna. Also, we can see the 3D electric field of the antennas. You can also animate the electric field by simply right click, you set animate versus phase. So now we can see the animation of electric field. Also, we can see the magnetic field. Again, if we right click, set animate versus phase. Yeah, so now we can see the animation of the magnetic field. Also, we can see the SIR value of the human body. So to create such plot, you simply right click, you set fringe, and then from here we choose for instance SIR, and then we want it for instance to be on the human body. So we choose human body and then we click OK. Yeah. So now let's look at the performance of the antenna with radome. So for this, this is the antenna again. I need to show the radome. So this is the radome, which is made of material which has permittivity of 2.9 and loss tangent of 0.02. Also we can show the car. So now we can clearly see that the shark antenna with radome on the roof of the vehicle. So now let's study the return loss of the antennas with and without radome. So for instance, here we can see the performance of GPS antenna with and without radome. Similarly for V2V and Wi-Fi antenna. So to compare results between two studies, you simply right-click with a 2D plot. So now let's say, for instance, we want to study the performance of GPS antenna with and without radome. So we'll choose without, S11. So here you go. And now we can see the performance of GPS antenna. Lastly, let's look at the 2D polar plots of the antennas with and without radome. First, let's start with GPS. So now we can see the performance of GPS antenna with and without radome. Next is the Wi-Fi antenna. And lastly, we have V2V antenna. So to create such plot, again, you right-click, say polar plot 2D. Let's say, for instance, study the one of Wi-Fi. This is width. Also, we can study the SIR with radome. Here comes the end of the live demo. So to summarize, you have gained insights into the challenges associated with design of shark fin antennas. We have demonstrated you the importance of using 3D EM simulation software such as HFWorks in ensuring reliable and efficient shark fin antenna operation in the automotive environment. With that, I would like to thank you, and now the floor is open for questions.